Now, coming to you live from my kitchen table, Foundations of Math and Pre-Calculus 10. Dance. 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 Today, Chapter 3, Factors and Products, Section 3.1, Factors and Multiples of Whole Numbers. Hi guys, welcome back. Well, we're going to start today with just a whole whack of definitions basically, and probably just reviewing some things that you've seen in the past, but we just want to make sure that we are all operating from the same starting point here. So first of all, I wanted to identify what are whole numbers, and before I can talk about whole numbers, I have to back up and say what are the natural numbers. So the natural numbers are also known as the counting numbers. They're the first numbers that were invented for purposes of counting, and they are 1, 2, 3, 4. You get the picture. They're all positive numbers used for counting. Then we have the whole numbers. Now these are essentially just the same as the natural numbers, but with one extra number added in, that number being 0. So we have 0, 1, 2, 3, 4, 5. 0 is not a positive number. It is not a negative number. It is neutral, like Switzerland, but less chocolatey. Next term to define, factors. Factors are two or more things that are multiplying each other. And product, this is of course the result or the answer that you get from multiplying two or more things. So for instance, in the statement 6 times 8, 6 and 8 are factors, and the product is of course 48. Interesting and worth noting, of course, that not only are 6 and 8 the factors of 48, the things that multiply to give you 48, they're also said to be divisors, right? Where a divisor is something that divides evenly into another number. Moving on, a prime number. A prime number is said to be any whole number that has exactly two unique factors. Two, no more, no less. This is a prime number. The two factors are always 1 and the number itself. So for instance, 5 is a prime number since its only factors are 1 and 5. Note that 1 is not a prime number since it only has one factor itself. Here's a list of the first 12 prime numbers. 2, 3, 5. I'll let you read them for yourself. And of course the prime numbers actually keep on going, and there's quite a lot of interest around prime numbers and their uses, which maybe aren't apparent right now, but we will talk about them in class when I see you. Note that the number 2 is actually the only prime number that's even. Can you think of why that might be? Next definition, composite number. Any non-prime number larger than 1 is said to be a composite number. So if it's not a prime number but bigger than 1. This is because it is composed of more than two factors. Example 12 is a composite number because it has more than two factors. Next definition, prime factorization. The prime factorization of a number is when you write a number out as the product of all of its prime number factors, and we'll take a look at an example of that now. Consider the prime factorization of 12. This is, of course, 12 is equal to 2 times 2 times 3, those prime numbers that multiply to give you 12. That's pretty easy for something like 12, but what about something like 1320? How do we do this? Well, my preferred method for doing this is as follows. I like to put the number 1320 like this and put a bracket like this. Kind of looks like when you did long division, except it's upside down. And we're actually going to do something quite similar to long division. I'm going to take 2, the smallest prime number. I always start with the smallest prime number, and I can see that 1320 will divide by 2 because it's even. 1320 divided by 2, if you know it, that's great. If you need a calculator, that's fine, but the answer is 660. Again, I'm going to put another L bracket here. 660 will also divide by 2 because it's an even number. 2 goes into 660 an even number of times, giving me 330. 330, I can divide that by 2. 2 goes into 330 exactly 165 times. Now, 165 is not going to divide nicely by 2, but it will divide evenly by 3. So I can put a 3 and say 165 divided by 3. This is going to be 55. 55 is not going to divide evenly by 3, so I go to my next prime number, which is 5. 5 goes evenly into 55, which gives me 11. 11 is a prime number. And if you look down the left side here, I've got a list of all the prime factors of 1320. So I can say 1320 is equal to 2 times 2 times 2 times 3 times 5 times 11. Or better yet, since I've got three 2's multiplying each other, I can use exponents to say this is 2 cubed times 3, there's only one of them, times 5, there's only one of them, times 11. And we have carried out here a little method to get the prime factorization of 1320. And our next definition, the greatest common factor, or the GCF. The GCF of two or more numbers is the greatest, or the largest, factor, or you could use the word divisor. It is the greatest factor that the numbers all have in common. So for example, determine the greatest common factor of 360 and 450. What's the biggest number that divides evenly into both of those? 360 is actually 2 times 2 times 2 times 3 times 3 times 5. I've skipped ahead a little bit in my working here. And 450 turns out to be 2 times 3 times 3 times 5 times 5. And what you do to get the GCF is you look at what do these two numbers have in common as far as their prime factors go. Notice they both have a 2. So we'll put that down as something they have in common. Now 360 has a couple of more 2's, but 450 doesn't, and we're only concerned about what they have in common. So I'm going to ignore those 2's. But 360 has two 3's, and so does 450. So we're going to take 2 3's, because that's what they have in common. And then again, they both have a 5 in common. 450 has an extra 5, but as far as what they have in common, it's 2, 3, 3, and 5. And now I can multiply these out. 2 times 3 being 6, 6 times 3 being 18, and 18 times 5 being a large number. No, I'm just kidding. 10 times 5 is, of course, 50. 8 times 5 is 40. So 18 times 5 is 50 plus 40, or in other words, 90. The greatest common factor of 360 and of 450 is 90. The lowest common multiple. Now, if this reminds you of lowest common denominator, that's because they are very closely related ideas. Well done. The LCM of two numbers is the least or smallest number that is evenly divisible by your two given numbers. Let's look at an example. The LCM of 3 and 5 is 15, because 15 is the smallest number that can be divided evenly by both 3 and 5. Okay? So for example here, find the lowest common multiple of 12 and 18. One method of doing this is just to list out the multiples of each number and find the first or the smallest number that's the same in both lists. So if you consider 12 times 1, 12 times 2, 12 times 3, and you get your list of all of the multiples of 12. And then the same thing for multiples of 18. So you've got 18, 36, 54, 72, and so on. And you look for the first number that's the same in both lists. Well, in this case, it's right here. It's 36. That wasn't very difficult. This method works quite well if the lowest common multiple happens to be relatively small, but it isn't a very convenient method for numbers that aren't quite so small. Let's look at the second method now, using the prime factorization of both 12 and 18. Again, 12 comes from 2 times 2 times 3, or in other words, 2 squared times 3, and 18 comes from 2 times 3 squared. So to get the LCM, we look at each of the prime factors here. We look at the prime factors for 12, we look at the prime factors of 18. and we use whatever is the biggest exponent for each one of those prime factors. So they both have a 2, but the biggest exponent is with 12 where it has 2 squared. So we're going to use 2 squared. And they both have a 3, but the biggest exponent on the 3's is with the 18, so we're going to use the 3 squared, and that gives us 36. Find the GCF and the LCM of 22, 36, and 8. So first, prime factorize everything. 22 comes from 2 times 11. 36 is 2 times 2 times 3 times 3, or 2 squared times 3 squared. And 8 is simply 2 cubed. What's the GCF of all three of these? Find what they have in common for factors. They all have a single 2 in common. 8 and 36 have more 2's, but 22 just has the 1. So the GCF is simply 2. That's what they have in common as factors. Now the LCM. Let's go again with the product of the greatest power of each prime factor. So 2's. Well, 8 has 2 cubed, so we're going to use 2 cubed. And as far as 3's go, well, 36, that's got 3 squared, so we need 3 squared. And there's no 5's, no 7's. Oh, there's an 11. 22 has an 11. It's just to the power of 1, so we'll just use a single 11. And then multiplying 2 cubed times 3 squared times 11, or in other words, 8 times 9 times 11, gives us 792. Now, if you were to do this by listing out the multiples of these numbers, right, going 22, 44, 66, 88, just imagine how long this is going to take you to get all the way to 792. Then you would have to do the same for 36. You'd go 36, 72, 108, and so on, again until you get to 792. And you would have to do the same with 8, 16, 24, 32, until you got to 792 to find that that was the first number that occurred in all three of the lists. And now, time for everybody's favorite part of the show, Two for You. If you were subtracting 11 over 4 minus 5 over 18, what would you use for the lowest common denominator? And number 2, David has a whole bunch of rectangles that are 24 by 56. That's pretty special. What is the smallest square that he can make out of them if he lines them up the same way? So he puts all of the rectangles this way, side by side. Maybe he has to put 2 rows of them. For answers to these questions and more, come on into class. Until next time.